Hey, I bet you didn't realise a lot of matrix type structures floating around in our world already, aren't there? What about these sorts of formats here? They look like a matrix. Down here, let's have a look at the shopping list. And then if we abbreviate it, remember, this is what we did last time with systems of linear equations. We didn't use x, y's and z's. We just took out the important numbers. So we're starting to abbreviate it a bit here. But this is the real matrix form. A matrix is an array of numbers, nothing to do with letters. And when you make them up, you need to remember the meaning of every entry here, because it's an array of numbers. So this is really the only matrix form there. And we've picked out the important numbers: 2 loaves of bread, 1 carton of juice, 6 eggs, 1 cheese. So, arrays of numbers which have unique meaning for each entry. Okay, what about this? A furniture inventory. What you've got in your flat, a unit and a house. A list of chairs, tables, beds and so on. So you could make up this summary, but the matrix really is this. And we put this squared off bracket at the end. And now you must remember the unique meaning of each of those entries. And they can't be played around with. You can't sort of add the 6 and the 1. No, because that's 6 chairs and 1 table in first row. Come over here, is flat. That's in the flat. Okay, so interesting stuff. You can see where we're going, can't you? We now need to look at the mathematics of combining matrices and the appropriateness of it. I think we've just seen the birth of a new area of mathematics here. Matrices and matrix algebra. Like, once we have these things, can we add them, can we subtract them, and all that sort of stuff. So let's go and look at the mathematics of matrices. First of all, we might just have a look at some mathematical descriptions. How do you want to describe that this is a long skinny matrix? I don't think long and skinny makes sense, mate, in mathematics. It's got 4 rows and 1 column. There's the rows, 1, 2, 3, 4. It only goes across this way, columns once. So we call it a 4 by 1 matrix, or a column vector, or a column matrix. It's only got a column. And then this one here has 3 rows and 3 columns. So it's a 3 by 3 matrix. And this one down here has got 1 row, but 1, 2, 3, 4 columns. So it's a 1 by 4 matrix, or a row matrix, or a row vector. Okay, so this is important now. We're starting to build up a bit of mathematical notation or terminology to describe what we've got. We don't want to put it all in words. Let's come down and have a look at the definition now of what we want here. So if we have an M by N matrix, that's a nice way of saying we've got M rows and N columns. And if I drew it, what would it be looking like? Well, let's make it slightly different here. So here, coming up here, would be, how many would there be? There would be M rows, and coming across here, don't know how many N is, there would be N columns. So that's the idea, and so we call that description the order of a matrix. So the order of a matrix has 2 components. The number of rows by the number of columns. We're not timesing them, but that's the way we put it there. Rows by columns. All right, so there's the first bit of matrix mathematics, I guess. Now we've decided to use this form for important numbers, an array of numbers, a matrix of numbers. We're going to go and start describing it and seeing what we can do with it. So come down here then and let's look at an example. Here's one here. Lisa goes shopping at store A to buy 2 loaves of bread at $2.65 each, 3 litres of milk at $1.55 and a 500 gram tub of butter. So the quantities are in a row matrix 2, 3, 1. You must remember their uniqueness. Okay, don't forget the numbers in an array stand for something different in every problem. Okay, so here then, if you looked at that, that would be the quantities matrix. The cost matrix is what we might put it this way. Just remember that it's cost of bread, milk and butter. Notice we don't write those when we're just in matrix land. That's just to remind you of what the row matrix is. It's a quantities matrix, and the column matrix is the cost matrix in a certain order. You must remember each entry is unique, so that implies order is important in a matrix. You must put them in the order that is meaningful and defined by your matrix that you've chosen to define. Okay, so if Lisa went to a different supermarket and found the prices were different here, so instead of the prices at store A, 265, 155, 235, the prices are now 225, 150 and 220. Must keep them in the same order. So now we're developing what? A cost matrix. Okay, but we're enlarging it to do different stores. Now, this is my big thing about matrices. Matrices are very easily expanded. This is very important. One of the big uses of matrices is, in my words, Huddy Maths, expandability. Ability, isn't it? Expandable, yeah. Expandability. You can expand them as long as you remember the uniqueness of each entry and what it all means when you're finished. It's not just a mass of numbers. Each of those entries is unique and means something special. Let's go and look at that particularly. If I go in here, what's that mean? That is, and we generally don't write that down the side, that's and down the bottom here, that's the price of milk at store B. Okay, every entry is unique. What's this? This is the price of butter at store A. This is going to be interesting as we go on and try to apply matrices. Matrices are very important in analysing large amounts of data. Okay, let's go down and have a look at some problems for you now. Write down the order, that's okay. Make up an inventory matrix, if you like, a list of goods. Can you imagine what Bunnings would be like? How would you summarise all the items in all the Bunnings stores? Okay, could you matricize that? There's another word. That's not a math, that's a Huddy Maths word again. Matricize. I like it. Then again, Huddy would. Matricize means to make a matrix out of the data. That's not a mathematical word, that's Huddy Maths. Okay, but anyway, you could think of that. And so they're going to ask you to matricize some of these things. There, make a matrix there, mate. Summarise that. And as we go down, here we are, trying to work out a pattern that we can use to summarise the unique value of each number mentioned there. Okay, well, have a go at those. I'll just bring those up there so you can do those. And pause the presentation, come down, let's look at the answers here. So we'll just put those down there. And of course there might be different ways, you might think about this, different ways of organising your matrix, rows and columns. There aren't any rules. You could put it a couple of different ways around maybe. So think about that. Okay, go back, do the problems, mark them, and then come along with me for the rest of the presentation now. Hey, you knew it was coming, didn't you? As soon as he said a new area of mathematics, I guess you knew we're going to have to define the mathematical operations which are possible between these new creatures, these matrices. What can you do with them? Okay, so first of all, can matrices be equal? Well, I guess they can, if all the entries match up. Because we said the entries in a matrix have a unique meaning. These crosses here are numbers. Okay, not x's, they're entries, and that entry there has a particular meaning. So if you want two matrices to be equal, they must have exactly the same order or shape, and the corresponding positions must be equal. I'll just bring in a notation that isn't used in this book, and of course I'm back there with Hayes and Harris, and it's not a bad textbook if you've got a copy of that. The screen clippings are from there. So if I was to refer to, let's have a look at this entry here. This is actually row 2, column 2. So in matrix A we call it A22. What do you reckon this one is in matrix A? It's A, and what's the row? Third row, third column. What about this entry here? This is A, second row, first column. So we do have a notation you see later on in maths, not so much at this level, to actually describe the element or item in a certain row and column position. We call it an element of the matrix. So here, all elements must match up. So if these two matrices over here are going to be equal, because you know that position is special, and if the matrices are equivalent, this must mean exactly the same thing, and to be equal, they must be exactly the same value. So those parts are like, I suppose, where have you seen this? Equating numbers before. Things like rational, irrational parts in other areas of maths. A plus B root 2 equals 3 plus 5 root 2. You know that A must be 3. That's a unique position in numberland. That's a rational part of this number. And B must be 5, because that's the irrational coefficient there. So because those two positions are quite different in numberland, then they have to be kept separate. You must equate the parts. So here we are over here. B's position must equal this because they're unique and special. Do you get the idea? Okay, so we can compare matrices and see what we can get there. We can also, can we come down and add matrices? Well, I reckon you could already have worked that out. And that is, if you are going to add stock to your store. So here's her stores. Sally's got 3 stores, got dresses, skirts and blouses. So in store A, that's how many of each she's got. Store B, yep. Store C, 68 dresses, 79, etc. Now, some new stock has arrived, and each store has 20 dresses, 30 skirts and 50 blouses must be added. So here, the new levels would be at each store adding 20, 30 and 50 to each store. Well, there's another way of doing it. You could say this is the current matrix and this is the top-up matrix. The top-up matrix in store A is going to have 20, 30, 50 added. Store B is going to have 20, 30, 50. Okay. So can you see it is appropriate because that is, what is that? That's store C, number of skirts. It is appropriate to add that to that entry there because the unique position of these two mean it's store C, skirt position. So store C, skirt position is that, and now there's 109 of them. So as long as everything matches, remember, unique meaning for each element in a matrix here. For each entry, unique meaning. Okay, so let's look at the little rule down here. So to add two matrices, they must be of the same order. That is, same number of rows and columns, same number of elements. And then we simply add the corresponding elements. Okay. Must make sure, because of the unique meaning of each element, that you are not crossing over and adding up skirts and dresses. You wouldn't like to confuse your skirts and the dresses, would you? No. Bad. All right, so let's go on and have a look at doing some problems there. So here we're going to just practice adding matrices and so on. So let's have a look. If we try to add A and B, first thing we check is they all match. Yeah, these are both 2 rows by 3 columns. Let's get used to that notation. So we're adding up the corresponding elements. So here we are. We can do that, and all matches, and we come down there. If you try to add A and C, you know you're in trouble because C is a 2 by 2. So there aren't corresponding positions here. Clearly, the entries in C mean something different. So it would be inappropriate to add it to A if you're looking at a contextual thing. But because they have different sizes or different orders, the meaning of each entry or element cannot match, so you can't do it. All right, let's go and do some. Oh no, not yet. We've got some multiples first. Sorry, forgot about that. Multiples. If we had 6 cans, 4 cans and 8 cans of peaches, apricots and pears, there's our matrix. No letters, remember, in matrices. Matrices are arrays of numbers, and you must keep your wits about you throughout to make sure you remember what the number means in each position. Okay, so if you double the amount in your pantry, you would have to double each of those. So that would be like adding another C to it, or saying it's 2C. So we could multiply each entry by 2. So 2 times C equals 2 outside of this. Now we don't have to worry about the 2. We call this a scalar actually, because it's just a multiple. The order isn't important, but the order is important here, isn't it? So in a matrix has an array of numbers where the order and the setup is important. This number here is called a scalar, not a matrix, it's a scalar. So it's just a multiple of each of them here. Okay, and so we get 12, 8, 16. There's nothing magical about this maths. It's just simply developing now that we have chosen to use arrays to summarise information. Let's have a look at 3C. Will be C by C by C. Well, it'll be 3 lots of each of them. Do you get the idea? A half C. Could we halve everything in the pantry? Yeah, well, as long as it's not 3 cans. Have trouble halving 3 cans. There'll be a mess everywhere. We cut that in half. Don't worry about it. Let's go on. Okay, so here we go. If a scalar T is multiplied by matrix A, the result is matrix TA, and you multiply every element of A by T. Okay, that's reasonable. Always base your understanding in what does a matrix mean. Do not start to forget what these entries mean, whatever they are, in whatever context. 1, 4, 7. Don't get wrapped up. These, you have to say to yourself when you're working with matrices, what could that mean? What's the context, perhaps, of that matrix? Because there's a lot of practical situations, and Hayes Harris do mention some of these. I reckon the best way of thinking about a matrix and the usefulness of it is the inventory matrix or inventory matrix, where you're making lists of how much you've got in store A, B and C of various items. So it's a good way of summarising for stock control. Okay, and of course you can use technology to combine matrices, and that's the next presentation in actual fact. How to use, well, a calculator, or you could use a spreadsheet to actually combine matrices. Alright, can we go down now and look at some little problems for you? So here's question 1 to 4. I think it's probably pretty important to do all of these just quickly and have a look. Okay, so that's question 1 through 4. For each presentation, have a look as usual. 5 and 6 and 7 there. And we're doing a bit of matricizing here. All right, 2-column matrices and so on. And then we'll go down to 8. Oh, it's going to fit 8 and 9 on. No, we'll go to 8 and 9. Okay. So I think it's pretty important to do most of these. and 10 and 11. All right, so 10 and 11 is a bit more theoretical, not actually providing a context for any of these matrices here, not saying what the entries mean, but just keep in mind each entry has a unique meaning. No playing around with changing positions and stuff. Each element or entry has a unique meaning, so keep that in mind when you're adding matrices. All right, let's go down and look at the solutions now. So here's question 1 and 2. I'll freeze it there. Coming down then, question 3. 3 through to 6, you can probably get there. And then question 7, 8, 9 and 10. Just pop down here and go to question 11. We can fit it on. Yep, we can fit that on. All right, so rewind the presentation each time. Have a go at all of them. Check your answers. Okay, let's go on now and see what more we've got happening. Is it possible to get a zero matrix? Oh, what does that mean? For real numbers, if you have a number A and you add 0, it doesn't matter which way around you do it, addition is commutative, isn't it? Commutative, doesn't matter which order you add things in. So then you still get A back again. No matter what A is, 0 doesn't do anything to it. Can you add a 0 matrix to a matrix? Well, if you're going to add them, the elements must match. Elements must match. So it's got to be the same size. Okay, it's got to be the same size. Here, therefore, if this is a 2 by 2 matrix, your 0 matrix must have a matching entry for every other one. So that would mean the 0 matrix must have all elements equal to 0. So that's the 2 by 2 0 matrix. This is the 2 by 3 0 matrix. So, same idea here. Notice they're using bold capitals in Hayes and Harris here to designate matrices. Now, they do use the same sort of thing, bold print, to designate vectors in mathematics. It's not in this course, but you usually use something like this, squiggle or a squiggle underneath or something, and you could use a bold print as well in textbooks, but you use lowercase letters. So here they're using capitals and bold to indicate matrices. So when you see that, it's not 0, it's a 0 matrix. Okay. All right, let's go down and have a look at some more then. What about negative matrix? Negative matrices. Can you see, I promised you before, we had started on a new idea, and that was arrays of numbers or matrices, and we need to follow that up with doing something about them. Can you add them and subtract them? And we're going to do lots of interesting things. So a negative matrix, if you multiplied it by a negative. Well, if we thought of the negative in this context as meaning -1, then it's the same as a scalar multiple, isn't it? You'll multiply every entry by that number out the front. Just as we did before, if we had 1, 2, 5, 7, 3 and 4 and multiplied it by 2, we're going to do this. We had a look at scalar multiplication before. So the neg1 behaves in the same way, and you're going to get this matrix here. So you can say it's simply reversing the signs of each element. Yeah, well, I'd rather think of it as multiplying each element by -1. So here, if you then add them, because of the properties of addition, of course, adding the negative will give the 0 matrix there. So that's really the properties of addition. 3 plus -3 has to equal 0. and neg1 plus 1 has to equal 0. So when you add the negative matrix, obviously, the addition of each element produces 0. So we can have this rule now. So can you see we're sort of developing some algebra rules in matrix land. It's matrix land because that's a bold, dark, that is, capital A. So we're talking about matrices there. And the equivalent in real numbers would be, say, A plus the negative of A is the same as the negative of A plus A, and it would be 0. Well, that's if A was a real number. A is a member of R. The big A's here are to indicate that these are matrices. So it is going to be possible to develop some algebra rules in what we're allowed to do in matrix land. And that's going to be quite an interesting component of this course. Okay, let's go down now and have a look at the summary here of the algebra for addition, comparing it to ordinary algebra. If you have two real numbers, when you add them, you get a real number. If you have two matrices, then when you add them, you also get a matrix. You can add A and B and put them in either order here. That's commutative rule in real number addition. And doesn't matter which way round you put matrix A and B if you're going to add them. No, well, can you see why it doesn't matter? You have, let's say, A1, A2, A3, A4, B1, B2, B3, B4. When we add them, it's A1 plus B1. Well, it doesn't matter if we add them in that order or that order, because we're adding elements. Hang on, B2. We're adding elements, and elements are just numbers. So we go back to the idea that if you're adding up elements, the commutative rule for addition says it doesn't matter which order you do it in. So because that's all matrix addition is, adding up separate elements, it doesn't matter which way around you do it. What about this rule here? This is associative rule, how you associate elements before or after addition. So if you add A and B in real number land, then add C, it's the same as adding A to B plus C already done. It doesn't matter which order you do that addition. So here we've got the similar rule in matrix land, because matrix addition follows very much addition of real numbers, because each element has to be added and they are just real numbers. And then of course we've done this rule here, adding of 0, that's got an equivalent, adding of a negative gives 0, adding of the negative matrix gives a 0 matrix. So it's interesting stuff that we are pursuing now, a new area of mathematics for you. So come down here and let's do the last set of problems. Explain why it is true that x plus a equals b. Well, if x plus a equals b, you could actually say this. If x plus a equals b, then x equals b, take a. Let's see if we can prove it. X plus a equals b. Now, if we add the negative of a, might be the best of that. Add the negative of a, slightly different. We're not really taking a away. We're adding the negative of a, and add to the negative of a to the other side. Then a matrix plus its negative is a 0 matrix, and that equals b plus the negative of a is b take a, and then therefore the final answer is x plus the 0 matrix is always just x. Okay, so can you see we are coming into working with, I suppose, matrix equations now. We have an approach of algebra with matrices that allows us to do equations. What about if 3x equals a, can you prove x is a third a? Well, let's start off with 3x equals a. Let's multiply this side by a scalar, a third a on that side, a third of 3x. And these are both scalars, so a third of 3 is 1x equals a third a, so matrix x is a third of matrix a. You might say, well, gee, that's obvious, that's what we do with real numbers. But no, it looks similar. We have to be careful here. Remember, when you do a step, that big A here is a matrix. not a number. So there will be some things that are different. The first thing here really is this over here. We're adding the negative of a. That's a better way of thinking it than subtract a from both sides, I think. There's a subtle difference there. So we'll come on to that later on, because what do you reckon? What do you reckon? Think, what's next? Multiplication and division? Hey, is that possible for matrices? That excitement, you have to wait and see. Okay, so come down and let's have a look at some exercises, and we'll finish there then. 10b2, simplify these. So I want you to think about, remember these letters now are matrices. Don't think they're just X's and Y's and B's and C's in our usual algebra for real numbers. No, no, no. This is matrix land. Is it possible to do the operations here? And is it possible to rearrange these things? What sort of considerations do you have to make because you're in matrix land? Okay. So I want you to go through each of those. It's probably worth doing most of them and then check your work. So what we'll do is come down now and have a look at the answers. I think, no, we can't get them all on there. It's question 1 and part of question 2. And then question 3 there. And that's it. So have a look at those things. Particularly look at how they do the rearrangements in question 2 there. That's very important. All right, I want you to pause presentation there and have a go. Build up your skill level. We've got a few presentations here that get very, very interesting, and you'll be glad to hear in this course that we're going to apply matrices in a very meaningful way to utilise this theory. And the next presentation is very exciting. I'll show you how to use the Casio 9860 Plus to do some of these calculations. At the moment, though, enjoy yourself, and it's cheers from me.